In this lesson, we will learn a new op-amp configuration called the inverting amplifier. We will learn as well a simpler method to analyze any circuit using op-amps. In the last lesson, we learned the non-inverting amplifier, which is a configuration that can amplify a signal but it cannot attenuate it. From the same circuit, we can derive the inverting amplifier. As its name says, it inverts the input signal. So if the input is a positive voltage, the output will be negative. The main difference between the inverting and non-inverting amplifier is the terminal to which we connect the input signal. As you can see, in the non-inverting amplifier, we connect the input signal directly to the positive pin of the op-amp. In the inverting configuration, we connect the input signal into the resistor R2. The positive pin is connected to ground. Let's perform the analysis in order to obtain the design formulas for the inverting configuration. We start with the basic op-amp equation. Since the positive pin is connected to ground, we can simplify the equation to the following formula. We need to obtain the voltage at the terminal Vn. To do so, we use nodal analysis. One important thing to remember is that the current into the op-amp is so low that it can be ignored. Therefore, we have a simple equation where the current that flows through the resistor 2 is the same as the current in the resistor Rf2. We use Ohm's law to write the equation in terms of the voltages. Then we can solve the equation to obtain the voltage Vn, and we replace it into this equation. Once we have replaced the value, we can solve for Vout. We can see that this equation still depends on the amplifier gain G. We will calculate the limit when the amplifier gain tends to infinity in order to simplify the formula. Here you can see the result. When the amplifier has a very large gain, we can approximate the formula of the inverting amplifier to the following. The gain is the ratio of the resistor Rf and R2. And notice the negative symbol. The output voltage will be inverted. Another interesting thing is that this configuration can attenuate the input signal. Selecting the appropriate values of Rf2 and R2, we can achieve either amplification or attenuation. Below you can see the simulation results of this circuit. When the resistors R2 and Rf are 1 kΩ, the output signal is a copy of the input signal, but negative. Before proceeding, let's make a small experiment. If we take the original op-amp equation and we rearrange it in order to calculate what will be the voltage value at the negative pin, we obtain the following equation. If we take the results we obtained for the non-inverting amplifier we saw in last lesson and put them into this equation, we can see something interesting. The input voltage Vp was 1 volt. The output was 2 volts because there was a gain of 2. And the amplifier gain was some large number like 100,000. We can see that with those values, the voltage at the negative pin turns out to be very close to 1 volt. If the gain is even higher, what will be the voltage at the negative pin? For example, in the case of an ideal amplifier that has an infinite gain. If we calculate the limit when the gain G tends to infinity, we obtain that the voltage at the negative pin is the same value as the voltage of the positive pin. An op-amp with very high gain is always trying to make the voltage of the positive and negative pins the same. The realization that the op-amp tries to make the voltage of the pins the same explains why the voltage follower works. When a voltage is received at the positive input, the only way that the two pins have the same voltage is if the output provides a voltage equals to the input voltage. When analyzing circuits with op-amps, we can make the following assumptions. First, the voltage of the positive and negative pins is the same. Second, the currents into the positive and negative pins are 0, therefore there is no current. These assumptions will help us make the analysis simpler. Let's do again the analysis of the inverting amplifier, but now using these assumptions. Here we have the circuit. We can see that the positive pin is connected to ground. Therefore, Vp is 0 volts. Since Vn must be equal to Vp, that means that Vn is also 0 volts. We write again the nodal equation for node V2. Since the current into the op-amp is 0, we have the following equation. Notice that I have already replaced the voltage of Vn and Vp, which is 0. For the current IR2, we have V2 minus 0 volts divided by the resistor value. And for IRF2, we have 0 volts minus V out over the resistor value. We can easily solve for the output voltage and we obtain the same formula as before. It is important to notice that with this analysis, we did not have to calculate the limit when the op-amp gain tends to infinity. When the positive pin of the op-amp is connected to ground, it is said to have a virtual ground. The inverting amplifier can be simplified to the following circuit. In the diagram, we can see the virtual ground. It is called like that because it's like having the circuit connected to ground, but no current flows, so it is not really connected. We will use this analysis trick in subsequent circuits. Now let's analyze the non-inverting amplifier using the assumptions we defined. The non-inverting amplifier can be simplified to the following circuit, which has a virtual connection. The voltage source V2 is defining the voltage at the node Vn, but it is not really connected because there is no current. The equation for the node V2 is the following. IR2 is equal to 0 volts minus the voltage of the node Vn, which we know it is V2, then divided by the resistor R2. And that current is equal to IRF2, which is V2 minus V out over RF2. From this equation, we solve for the output voltage and we obtain the same result as before. Reiterating, we did not have to calculate the limit when the amplifier gain tends to infinity. As a summary for this lesson, we learned the inverting amplifier configuration. In this configuration, the gain is defined by the ratio of the resistor RF2 and R2. The output voltage is negative and we can either amplify or attenuate the signals. We also learned how the op-amp behaves when the gain is very high. This makes possible to consider the following assumptions when analyzing an op-amp circuit. The voltage of both pins will be the same and the current into the op-amp is 0. Using these assumptions simplifies the analysis of op-amp circuits.